Thanks. It's nice to have the opportunity to be here. So I'm going to talk about some joint work with Louis Esperet, František Kardoš, Dan Kral, and Sergei Norin that we did mostly in Prague, but also in Montreal and Princeton and Banff. So I'm going to be talking about perfect matchings in cubic graphs. And so this is a lot of stuff that a lot of people have probably already seen. So a cubic graph is a graph in which every vertex has degree 3. A bridge is the same as a cut edge, so it's an edge whose removal disconnects the graph. And a perfect matching is just a set of n over 2 disjoint edges. So you want to have a matching that covers every vertex. So why were people interested in the number of perfect matchings in a graph? For the case of bipartite graphs, the number of perfect matchings is actually the same as the permanent of the biadjacency matrix. And a lot of people in the 70s were interested in kind of investigating the difference between the permanent of a matrix and the determinant of a matrix. So in this context, perfect matchings were really interesting to them. So Verhoeven proved in the late 70s that for any bipartite bridgeless cubic graph, the number of perfect matchings in the graph is exponential in the size of the graph, so 4/3 to the power of the number of vertices over 2. And we'll actually exploit his approach in our approach. So just a couple preliminaries. Actually, it's impossible to have a bridge if you're bipartite in a cubic graph. And a perfect matching contains every bridge in a cubic graph. So this is easy to see just by a parity argument on the number of vertices on either side. And so that makes it really easy to construct an example of a cubic graph that has bridges but has 0 perfect matchings. So you see that a perfect matching would have to contain this edge and this edge and this edge, which is impossible. So that's why we insist that the graph has no bridges, because it's necessary. So Peterson, 120 years ago, proved that every bridgeless graph has a perfect matching, every cubic bridgeless graph. And this is a pretty elementary exercise. And you can actually easily show that every edge in a bridgeless cubic graph is in a perfect matching. So that means that every bridgeless cubic graph has at least 3 perfect matchings. And we want to prove that it has at least n to the epsilon for some universal constant, positive epsilon. So the Lovasz-Plummer conjecture, which was actually first posed in the 1970s but didn't appear in print until the mid-80s, says that there's a universal positive constant epsilon, so that any bridgeless cubic graph has 2 to the epsilon n perfect matchings. I'll actually, if I have time later on, I'll mention a more extensive version of the conjecture that they posed that our methods are completely useless for. So that's still open. So there are a couple of ideas that immediately come to mind when you start working on this problem. One of them is deleting 2 vertices. So what you would want to do is take 2 adjacent vertices, delete these 2, and then you've got a graph in which everybody has degree 3 except these 4 vertices that have degree 2. So you kind of want to add a couple of edges to make this graph cubic. And then you want to look at the perfect matchings inductively. You want to look at the number of perfect matchings in this graph. And there are actually 4 graphs that you can construct. And then if you can do this in a smart way and say that the perfect matchings in these auxiliary graphs correspond in a very sensible way to the perfect matchings in the original graph, then you can get a nice inductive argument. And that's how the proof goes for the bipartite case. So what's the problem with this? The problem is that when you make this auxiliary graph, you could introduce a bridge. And we can't have that. So the connectivity can drop by 2. So as long as we're cyclically 4-edge connected, or bipartite, by a parity argument, then we'll be okay. So the solution is to only use this approach when the graph is actually cyclically 4-edge connected, in which case it's an inductive step that's not going to ruin our argument. So that's the first idea that we steal. The second idea, I don't know if we steal it really, but it's kind of something obvious that comes to mind, is contracting one side of a cyclic 3-edge cut. So a cyclic 3-edge cut is just a 3-edge cut that has a cycle on either side. So if you're talking about a cubic graph, you don't want to talk about a trivial edge cut, a trivial 3-edge cut that just has one vertex on one side, because you can't reduce on it. So we don't really consider these to be cuts. So suppose we have a cyclic 3-edge cut with some non-trivial amount of stuff on this side and this side. And then we make 2 auxiliary graphs. One by contracting this side down to a single vertex, and one by contracting this side down to a single vertex. These are going to be cubic, because it's a 3-edge cut, and they're going to be bridgeless. It's easy to show that. So what we would like to do is we'd like to be able to say, okay, well, by induction, there's a lot of perfect matchings in this graph and a lot of perfect matchings in this graph. So we should be able to kind of glue them together. So kind of join these edges back together. And then multiply the number of perfect matchings in this graph that contain this edge by the number of perfect matchings in this graph that contain this edge. And then we can get some sort of multiplicative thing that will help us get an exponential bound. The problem with this is that that even if we know that these 2 auxiliary graphs have exponentially many perfect matchings, and we know that every edge is contained in some perfect matching, we don't know how these are distributed. So it could be the case that over here we have 10 to the 10, for example, perfect matchings intersecting this, and then just 1 over here and 1 over here. But over here on this side we have 1, 10 to the 10, and 1. So that when we multiply these together, we don't really get an advantage. We divide the number of vertices in 2, for example, and all we can do is add the number of perfect matchings together. So that's a bit useless for us unless we do something a lot stronger. So in certain situations, we're actually going to prove that every edge is contained in exponentially many perfect matchings. And in that case, when you multiply this by this, you will actually be guaranteed to get something big. So those are the 2 basic ideas, and we're going to combine them along with some ways of getting around the problems that arise. So back to the background. There was a long period of time when people were stuck on stuff between n and n over 4. So in the early 80s we had a bound of n over 4 on the number of perfect matchings. And then this was improved to n over 2 much later. And then 3n over 4. And then finally Esperet, Kardosh, and Kral proved a superlinear bound on the number of perfect matchings. So this is there's still some debate as to whether or not this is as big as n log n or n log log n or anything like that. But it grows faster than n, just not very much faster. So getting to the exponential bound is a big step. In terms of restricted graph classes, there are some situations in which it's much easier to prove the theorem. So Kardosh, Kral, Mishkov, and Sereni were able to prove it for Fullerene graphs. And a Fullerene graph is a special kind of 3-connected planar cubic graph. And they were able to come up with quite a short proof that the number of perfect matchings is exponential in the number of vertices. And a couple of years ago, Chudnovsky and Seymour proved that the theorem holds, or the conjecture holds, for all planar graphs. And so they proved n over a very large constant, which is not really important. I mean, getting to the exponential part is the important bit. But they actually did a lot of the legwork that we steal. And the most important part is to go from 3 edge colorings of planar graphs to fractional 3 edge colorings of non-planar graphs. And then kind of using probability distributions to get around the problems that arise. So we basically take most of our ideas from the proof of Voorhoeve for bipartite case, and the proof of Chudnovsky and Seymour for the planar case. So how are we going to generate a lot of perfect matchings? One obvious way is to find 2 perfect matchings, and we want to choose these 2 perfect matchings in such a way that we can generate many, many perfect matchings from them. So suppose we have a red perfect matching and a blue perfect matching in this graph, and their symmetric difference contains many, many cycles. And so these cycles are all going to be even and alternating between the 2 perfect matchings. So we can actually generate a lot of perfect matchings from these. Because if we look at the symmetric difference, we can just choose any subset of these cycles. And if we want to construct a perfect matching, we just take either the red or the blue. And so if we have k components in the symmetric difference, we have k cycles that we can choose from, red or blue, and so we get 2 to the k perfect matchings, just generated from these 2 original perfect matchings that have a nice symmetric difference. So how do we find these alternating cycles? This is what Seymour and Chudnovsky do. They use a result of Tate that tells you that because the 4-color theorem is true, every planar cubic graph is 3-edge colorable. And then you can use the color classes in this edge coloring to give you a nice selection of perfect matchings. It's not as simple as that. Actually, it's a little bit complicated. But because we can't use this 3-edge colorability result, we actually have to go to fractional 3-edge colorings, and then we use random matchings. So actually, it's not always possible to generate exponentially many perfect matchings in this way. Sometimes the girth is going to be too big. The girth is the minimum length of a cycle in the graph. So if we want to create exponentially many perfect matchings, we need linearly many disjoint cycles in the symmetric difference. But if the girth is as big as log n, we're not even going to be able to find linearly many disjoint cycles. So this strategy doesn't work all the time. So sometimes we can do this, and sometimes we have to do something else. So we prove that one of 2 things happens. In one case, we can choose this m and m prime so that the symmetric difference does have a lot of cycles in it. And if the number of cycles is linear in the number of vertices, then we're okay. But if that's not the case, then we're actually guaranteed that every edge is contained in exponentially many perfect matchings. So this is the notation we're going to use for this. M asterisk is the minimum over all edges of the number of perfect matchings containing that edge. And I already showed you that because of the girth construction, we don't necessarily have S2 holding. And this graph that I already showed you tells us that S1 doesn't necessarily hold either. So if you insist that this diagonal edge here is actually in the perfect matching, then you're forced to take this one, and then this one, this one, this one, this one. And so this edge is only in one perfect matching. So this is kind of the same problem that's going to arise here. And it actually turns out that graphs with this property have a very specific structure. You can actually build them from K4 by doing some expansion operation. But we kind of prefer to say that either we can do this or we can do this. And one of the more interesting parts of the proof is how we combine this into a single induction hypothesis, because they seem to be quite different statements. So remember, we're looking for two perfect matchings with lots of alternating cycles in their union. And so we want to look at notions of alternating sets. We actually want to find sets so that we can find an alternating cycle in each of them. And since they're disjoint, we can just take our pick. So we define the first notion of an alternating set in the constant of a fixed perfect matching M. And so X, we'll call this X here. X is alternating if there's a second matching, M prime, so that outside of X, M and M prime agree. And inside X, there's at least one alternating cycle between M and M prime. So as I said before, it's sufficient to find a large collection of disjoint alternating sets for some M. But we don't know how to find this directly, so we're going to use the probabilistic method and properties of the perfect matching polytope. So let's talk about the perfect matching polytope a little bit and probability distributions on perfect matchings. So there are three things that you can conflate here. The first is edge weightings with certain properties. The second one is fractional edge colorings. And the third one is probability distributions on the set of perfect matchings. So if we have a non-negative edge weighting on the Bridgeless cubic graph, we say that it corresponds to a random matching M sub W if for every edge, the weight on the edge is actually the probability that that edge is contained in the random matching. And so if you can actually make this weighting using a convex combination of perfect matchings, then you're going to be in good shape. You're going to be in the perfect matching polytope. So that's the set of edge weightings with at least one corresponding random variable M sub W in the set of perfect matchings. So these edge weightings need to have certain properties. And let's consider what are some obviously necessary conditions. So how many edges does a perfect matching have incident to a given vertex? Exactly one. So the first condition is obviously the weight on an edge needs to be between 0 and 1. The second one is that around a vertex, the sum of these weights needs to be exactly 1, because anytime you take a perfect matching, you're going to hit it with exactly one edge. So we're just taking the properties of a perfect matching and taking the fractional version of them. Oops. And the final thing is that every time you have an odd cut, a perfect matching is going to have to cross this cut at least once, just because of a parity argument. So if you add the weights on the edges of an odd cut, then you get at least weight 1. So for example, the uniform vector 1/3 is always in the perfect matching polytope, and you can easily confirm that. And so this is equivalent to saying that every Bridgeless cubic graph is fractionally 3-edge colorable. So you just take the weights on the probabilities of the perfect matchings in the distribution corresponding to this weighting, multiply them by 3, and that gives you your fractional edge coloring. So this is a really old result of Edmonds, and it's extremely useful for what we want to do. So remember, the first notion of an alternating set is something that we define. We fix an M, and then it's an alternating set if there's another matching M prime so that the two matchings are not the same and their difference is contained in X. So what if we start to define alternating sets with respect to edge weightings? So given an edge weighting W in the perfect matching polytope, we want to take any random variable in the set of perfect matchings corresponding to the weighting and say that the probability that we have our set X being M alternating is at least a third. And we don't need this to be a third really, it just works out well. We need this to be some fixed constant greater than 0. And because we're using a random variable, it's actually M sub W alternating. But even this doesn't do everything that we want to do, because we want to analyze edge weightings in a very local way. So we basically want to say, well, if the edge weighting does what we like over here, and the edge weighting does what we like over here, then we can kind of combine these two things in a way that doesn't interfere. Or sorry, if we have a good edge weighting here and we have a good edge weighting here, we want these to not interfere. So we come up with a third notion of an alternating set, which basically says that you can have a bunch of alternating sets that are disjoint and don't interfere with each other. So in this sense, we're going to talk about a set being strongly WX alternating. If we put a weighting on all of the edges with at least one endpoint in X, and then we just look at that, and we get a high probability of X being M sub W alternating. And we say X up here because we only define the weighting with respect to edges with an endpoint in X. So this is a little bit hard to follow, but basically what we want to do is define edge weightings on local sets, a variety of local sets that are disjoint, and then fill the rest in with whatever we want, which is actually going to be 1/3 everywhere, and then prove that each one, if we want to prove that there's a probability distribution on the set of perfect matchings, so that each one has a fairly high probability of being alternating.
Local sets are of size like N?
No, they should be of size, 6. They should be really small.
Oh, okay.
And so, well, not actually 6. We're going to kind of grow them at some point. Less than 100. Yeah. And then we kind of come up with a decomposition, and then we chop them off the decomposition in a way that I'll explain later. So don't read any of this, because I just told you what it means. It's totally confusing, and the only reason I put this on this slide is to say that the actual definition of this is pretty ungainly, but the explanation of it is relatively simple. We don't want these to interfere with each other. So a partial edge weighting Wx on E sub x is extendable. So what is this? We're taking an edge weighting on the edges with at least one endpoint in X, and then we want to say that it's extendable. So we put 1/3 everywhere, just because 1/3 is actually basically the sensible solution. And then we want to say that if we put a bunch of these together, then we can actually extend it into something that's in the perfect matching polytope. So it's basically a locality condition. So, burls and foliages. These are burls, and a foliage is a collection of burls, simply put. Oops. So a burl is going to be a small set of vertices so that we have some nice edge weighting, so that we can extend the edge weighting, and the edge weighting is strongly alternating. And remember what strongly alternating is. Strongly alternating is, it means that no matter how we extend the weighting to the rest of the graph, we have a good probability of getting an alternating cycle in here. So basically what we want to do, this says explicitly, we want to kind of take the union of these local weightings by taking the weighting on every set and then putting 1/3 everywhere else. And sorry, so a burl is one of these nice sets, and a foliage is a collection of them, disjoint. So if G contains a foliage of size k, then the number of perfect matchings in the graph is at least 2k/3. 2 to the k/3. So we basically take the foliage, which is a collection of burls. We take our weighting in the perfect matching polytope, so that covers the whole graph, so that locally on each member of the foliage we're W alternating. And then we just take a random matching and look at the probability of getting an alternating cycle in each burl. And by the definition, each burl is going to have probability at least 1/3 of having an alternating cycle. So there's a non-zero probability that we're going to have at least k/3 burls with alternating cycles. And that's all we need. So these are going to be the alternating cycles. And actually, C4 is a burl. This is the best and simplest example. So a burl is defined by putting the weighting on the edges and then putting 1/3 on everything that's sticking out of it, and then proving that we've got some high probability of having a nice alternating cycle in here. So basically, you're going to have an alternating cycle in a C4 if you have, well, you can't have more than 2 edges in a C4 in a perfect matching, so you want at least 2 edges in the perfect matching. And so just look at the expected number of edges in the perfect matching in the C4. It's just 1/3 plus 1/3 plus 1/3 plus 1/3, so 4/3. Therefore, the probability of having 2 edges is at least 1/3. And that's exactly what we need. So it might be a little bit hard to follow, but basically a burl is just something where we can define a nice weighting where we have a high probability of things going the way we want. And also the more important thing about burls is that we can kind of decompose them. We can rip them off the graph and close everything up and then apply induction. So a twig is a special kind of burl, and it's going to be a really trivial burl. So a twig is something that corresponds to a cyclic 2-edge cut, or a cyclic 3-edge cut where you have at least 5 vertices on one side. So this is going to be a twig, this is a burl, and this is the rest of the graph. Or it's going to be a cyclic 3-edge cut where you have the burl here and the rest of the graph here, and you have at least 5 vertices. And what does it mean when you have at least 5 vertices? It's cyclic, so it doesn't have 1 vertex, and it doesn't have 3 vertices, so you're not just going to end up with a triangle. For reasons I won't get into, triangles just don't really help you when you contract on them. Or say, yeah, I won't get into it, but they don't help you. They don't hurt you, but they end up being a waste of these 2 vertices that you contract away.
Sorry, I didn't understand.
A twig is a certain kind of burl. It's basically a special kind of burl that is very easy to remove from the rest of the graph and reduce on. So what we're going to do is we're actually going to contract this burl and apply induction on what's left over. And because we contract a burl, what we're going to do is we're going to contract a burl that's not too big. So we throw away a constant number of vertices, and then we make some gain in the number of perfect matchings. And the weighting gets a little bit complicated. We specify twigs because we give them bigger weight than other burls, because they're especially helpful and easy to deal with. So remember what M asterisk is. M asterisk is the minimum over all edges of the number of perfect matchings containing that edge. So we already know that every edge is in a perfect matching in a cubic bridgeless graph. So M asterisk is at least 1. And it's also easy to prove that it's a technical lemma, that it's at least 2 if you have at least 6 vertices. Oop, that should be there. And the graph is cyclically 4-edge connected. And if you have at least 6 vertices, you have at least 4 perfect matchings in the graph. And these kind of turn into base cases for our induction.
The last one is M star or M?
No, that's just M. So that's just the number of perfect matchings. M star, we don't even need it to be bigger than 2 because we only get rid of burls on a constant number of vertices. So as long as we can throw away a constant and multiply by 2, that's good enough for us. So as I mentioned before, what we want to do is construct 2 auxiliary graphs by a cut contraction. And actually, well, I think the battery's dying on this thing. So what I was saying is that if every edge is in 2 perfect matchings, then when you multiply these numbers together, each one is going to go up by at least 2. So you're going to get a factor of 2 in the number of perfect matchings. And so that's not going to help you if the size of G1 is equal to the size of G2, because you're going to divide the number of vertices in 2, and then you're going to put them together and multiply the number of perfect matchings by 2. But if you're able to insist that G1 has a small number of vertices and G2 has a lot of vertices, then you can actually get an exponential bound. And that's the basic idea. So what we do in the proof is we take this very simple idea and then we basically build a patchwork of methods of dealing with various problems that come up. So the ideas themselves are pretty simple, but the ways that we have to get around them are not always. And if we have a cyclic 2-edge cut, then we contract in a different way. To make G1, we just delete this side and replace these 2 edges in the cut with just a single edge. And so you might worry that this could even be a C4, so we're making parallel edges. But that's okay. We actually proved the conjecture for multigraphs. And they're not hard to deal with, parallel edges, so we don't even have to worry about them. So I was mentioning earlier that triangles don't help us, but they don't really hurt us. And the reason that they don't hurt us is because we can actually contract them one at a time. So suppose you have a perfect matching in the graph, and so this is a cyclic 3-edge cut. So we know that a perfect matching has either 1 or 3 edges in this cut. So suppose it has 1. I mean, if it has 3, it's not going to correspond to a perfect matching in the contracted graph, because you can't have 3 edges in the perfect matching. So we can just think about the ones that have 1 edge here. So if it has 1 edge, and this is not in it, this is not in it, then there's only 1 perfect matching that it extends to. So you have to pick this edge. So you're not going to gain anything by contracting a triangle and applying induction, but you also don't lose anything. So as long as we can contract away all the triangles without kind of destroying the entire graph, we just need to ensure that epsilon and vertices remain. Then we're okay. And this actually is not always the case. So let's see how fast I can go. Oh, there it is. So if you actually contract this, this will turn into a triangle, and you can contract again and again and again, and you'll end up with a C4 or a K4. So if you try to contract triangles until the end of time with this, you're going to lose. So instead, we just contract irrelevant triangles. And an irrelevant triangle is a triangle that doesn't share an edge with a C4 or a triangle. Or a digon. So in this graph, you can see that, that this triangle is actually relevant. And the nice thing about relevant triangles is that they turn into twigs. So here, the twig is going to be, you're going to put this triangle together with the C4 that it shares an edge with. And so these 5 vertices are going to form a twig. So remember, one kind of twig is something where you have a 3-edge cut. So this edge, and this edge. And you have at least 5 vertices. So there are a few different ways that a twig can arise from relevant triangles, and they're all easy to deal with. So if you contract an irrelevant triangle, you're not going to create a new triangle in the graph. So you can actually contract one, and then if there's another, you continue to contract one at a time until they're all gone. Every time you contract a triangle, you remove 2 of the vertices and leave 1 of them. So you're only going to get rid of at most 2/3 of the vertices, which is fine. So we're left with a constant proportion of the vertices. And these are the kinds of twigs that can arise when you have relevant triangles. So actually, we're going to make a small cut decomposition tree, which is a decomposition tree where the edges correspond to cuts and the vertices correspond to vertex sets. And we're going to do that so that every twig is a leaf and every leaf is a twig. So it's not trivial to show that this exists, but it's not that hard either. Okay, so as I said, we're taking 2 different ideas, and we're proving that we're taking 2 different statements, desirable statements that imply the result that we want, and we're saying that one happens or the other happens, at least one of them. It's not a dichotomy, but at least one of them happens. So what we need to do basically is we need to come up with a bunch of weightings for what we want and a bunch of constants so that, okay, FW is the foliage weight. So this is a weight that you get from putting some weight on twigs and some different amount of weight on burls that are not twigs. And so you get a foliage weight. And if you have a big foliage weight, you have a big foliage. And the graph has a core. Basically, if we can continue to contract on 2 cuts and 3 cuts and end up with something that's cyclically 4-edge connected and has at least 6 vertices. So if the graph has a core, then the minimum number of perfect matchings containing a given edge is at least exponential. So this is going to be some universal constant. So exponential unless we have a big foliage. And if we have a big foliage, we're fine. So that's how we combine the 2 ideas into one induction hypothesis. So the proof sketch goes as follows. If the whole graph is cyclically 4-edge connected, so we're proceeding by induction. If the whole graph is cyclically 4-edge connected, then we apply Voorhoef's splitting trick. And remember, this is the trick where we deal with, where do I keep on? We delete these 2 vertices and then reconnect to get a graph on n-2 vertices. And we lose some connectivity, but it's okay if we're 4-edge connected. So if the whole graph is cyclically 4-edge connected, then we apply the splitting trick. Otherwise, if we're able to split on a 2-edge cut or a 3-edge cut, into two graphs, each of which has a core, then we can actually apply induction. And we apply induction in, a variant of the obvious way. We basically say that when you glue back together on the cut, then M asterisk goes up in a nice way. You can just multiply them together, which is actually fairly obvious. And the foliage weight goes up in a nice way, except you lose a little bit. But beta in this case is so small that we don't even need to worry about it. Okay, so the case we're left with is the case in which you have a small cut decomposition tree and you have at most one big node. So you can't split the graph up into two big graphs that are nice to deal with. So we're actually going to have to look at the tree, look at the decomposition, and try to kind of pull pieces off the tree one by one. But first I want to show you the splitting trick. So we actually split on this edge and this edge, and we come up with 4 auxiliary graphs on n-2 vertices. And this is exactly what Voorhoeve does for the bipartite case. And since a bipartite cubic graph can't have a bridge, there are no worries about connectivity considerations. So you have G1, G2, G3, and G4. And you actually have not a bijection, but you can map every perfect matching containing a given edge in one of the auxiliary graphs to a perfect matching, a unique perfect matching, or a canonical perfect matching containing the same edge in the original graph. And so basically what you get is you have 4 times m of m of G1 plus m of G2 plus m of G3 plus m of G4. So you would be happy if m of G was at least this big, because you'd be throwing away 2 vertices and then multiplying the number of perfect matchings by 4. That's a big win. But this isn't actually the case, because you're going to double count. So some perfect matching in G2 is going to correspond to the same perfect matching in G that a perfect matching in G1 corresponds to. But this isn't going to happen with all 4 graphs. It's only going to happen with 3 of them for each perfect matching. So you're multiplying the number of perfect matchings by 4, but you're only overcounting by a factor of 3. So you throw away 2 vertices and you multiply the number of perfect matchings by 4/3. And that's all we need for the cyclically 4-edge connected case. Now, what about the case that isn't cyclically 4-edge connected and you can't split up into 2 big cores? So these are all going to be very small vertex sets, like 2 vertices or something like that. And these cuts are not necessarily going to be disjoint. So basically what you want to do is you want to start climbing up from a leaf, and you want to stop when you hit a node in the tree that has degree greater than 2. And then you want to rip off this subtree. And basically you want to prove that this is a burl. So you also want to prove that you can do this without taking away more than 100 vertices, say. So if there are many leaves, remember I already told you that every twig in the original decomposition corresponds to a leaf, or every leaf corresponds to a twig. So if you have a lot of leaves, then compared to the number of nodes in the tree, then you win. But it's possible that you have a tree that has many nodes and few leaves. For example, if the tree is a path. So what you want to do is you want to say, well, we have all these we have all these nodes in the path. This is a leaf. Some of these are going to be 3 cuts, and some of these are going to be 2 cuts. We want to say that if you have 10 3 cuts in a row, then you have a burl. Or if you have 3 2 cuts, not necessarily in a row, but in this path of vertices of degree 2, then you also win. So how do we prove this? We have to look at the possibility that we have 10 3 cuts in a row. And basically, we know exactly what this sequence of 3 cuts is like. It looks like 3 paths, R1, R2, and R3. And every node in the decomposition tree is going to correspond to 2 nodes here. It's just going to be an edge between 2 of these paths. So we're in good shape if we have a situation where we have 2 of these cross edges that go between the same 2 paths, and also the parity of the paths between them on either Ri are the same. So this is actually inevitable. It's definitely going to happen as long as you have at least 10 consecutive cuts. And then you just kind of you look at an alternating cycle here. You do the appropriate weighting on where every weight is 0, 1/3, or 2/3, and you can prove that you give a burl of bounded size. And the size is bounded because you have at most 10 cuts, and each cut is only 2 vertices, so you're talking about 20 vertices. And if we don't have 10 3 cuts in a row, and we take 32 cuts, then at least 3 of them are going to be 2 cuts. And we can actually prove pretty easily that if you have 3 2 cuts on a long path in the tree, then you're going to have a burl as well. So if we take a path of length 32, then we have a burl. So going back to the picture of the tree, if you have a tree with no paths on vertices of degree 2 of length 32, then the number of leaves is going to be some constant proportion of the number of total nodes in the tree. And that's exactly what we want. So the nuts and bolts, I'm just going to mention this really quickly. We choose a bunch of constants so that everything works out. And they tend to be a big mess, and we multiply them all together, and that's where we end up with 1/4000. So this is the theorem that we get. Any cubic bridgeless graph has at least 2 to the n over 3761 perfect matchings. And I'm just going to talk about the more general Lovasz-Plummer conjecture, which a lot of people don't actually know about, probably because it seems so much harder than the cubic case. But they conjecture that if you take a k-regular graph, there exist constants c1k and c2k, so that you have at least this many perfect matchings in a matching-covered k-regular graph. A matching-covered graph is a graph in which every edge is contained in a perfect matching. And furthermore, this is the hard part, we want C2 to go to infinity with k. So that's still wide open, and so many of the things that we use completely fall apart when we increase the degree from 3. Maybe some of the ideas could work, maybe not. But here's one partial result in the direction of this that we can do pretty easily. So if we insist that the graph is k-regular and k-1 edge connected, then we actually end up getting what we want, but this C2 doesn't go to infinity. So it's nowhere near the strength of the full conjecture, but it's what we can get by applying our result. So the fact that the graph is k minus 1 edge connected tells us that the uniform vector 1 over k is in the perfect matching polytope, because you're not going to have any odd cut on fewer than k vertices. So you take perfect matchings, and you take 3 perfect matchings, and you maximize the number of degree 3 vertices in their union, right? So probably some of you can already see where this is going. We can actually do this so that the union induces a large cubic graph. So sometimes an edge is going to be in 3 of these M1, M2, M3, in which case this is not really useful. Sometimes it's going to be in 2, and these 2 will be in 1 each. And we kind of reduce these away. But what we really want is when we have a vertex where we have M1, M2, and M3. And we can actually get a lot of those vertices just by looking at the expected number of them. And then we actually get a big cubic graph, a cubic bridgeless graph with a number of vertices sufficiently large. And then we directly apply the result that we get for cubic bridgeless graphs and the perfect matchings that we get from this auxiliary graph. They naturally extend uniquely to perfect matchings in G. So this is just kind of basically the first thing we can do about this broader Lovasz-Plummer conjecture, and the rest is wide open. And I'll stop there. Thanks.
Great, thank you very much. Do you have any questions?